Good afternoon, everybody. Before we get started, um, I've got an announcement, or rather, I've got someone who's going to be making an announcement. Hold on one second. I'm going to turn things over to them. Josephina, you should be able to unmute yourself. All right.
Perfect.
I'm going to put, you gave me a flyer. I'm going to put the flyer up. I'm going to share my screen while you talk, unless you want to put it up.
Oh yeah, I was gonna put it myself.
If you want to do it, it's all yours. Sorry. Take it away.
Yeah, I just need you to enable screen sharing.
Yes.
Should be on the bottom.
Oh yeah, it's going to make you co-host, but I guess I can do that too. Actually, let me just make you co-host to make it easier. All right, you should be able to do it now.
Awesome. And here's the flyer. All right. Hi everyone. My name is Josephina. I'm the project coordinator for the EMU study. It's a study under the Center for Children and Families at FIU. So as part of my program, we have graduate students who are working towards their PhD, and part of it is conducting their own research. So we are conducting a study that examines how people learn from everyday emotional experiences involving other people. And we're looking for participants ages 18 to 24 who are undergrad students at FIU and who have a reliable internet connection. So, for example, so we can use Zoom because all of our studies and sessions are done through Zoom. There's no in-person contact whatsoever. Um, so if you agree to participate, you'll be asked to complete some self-report questionnaires about how you think, act, and feel in various situations with other people. You'll also be completing some behavioral tasks that involve interacting with your peers and some behavioral tasks that allow you to earn some money. So the duration of the study, it's about 2 hours and it's broken down into two different visits. On the first visit, you'll be with us on Zoom for about 45 minutes, completing some questionnaires online. And then the second one will be completing some behavioral tasks online as well. And if you decide to participate, you'll be compensated on by two different ways. Option one is getting 2 cent credits, which can be applied to this class or another one, and up to $10 based on your behavioral task performance. And option two, it's cash only, and it's dispersed through Venmo, and it's $10 plus $10 based on how well you do on the behavioral task. And I don't think you can find the study on Sona yet. So what you can do is just email me or email one of my colleagues. His name is Logan. His email is right there on the flyer, but I will share my email with all of you. So I'll put it in the chat. Does anyone have any questions? No? All
If
right.
anyone has any questions, you can ask me and I can send them your way.
All right, wonderful.
All right, thank you very much, Josephine. Appreciate it.
Yeah, thank you so much for allowing me to present our study. Have an awesome class.
No problem. Thanks. Bye.
Bye.
Okay, and obviously remember that you can get up to 8 points of extra credit in this class, and I double whatever Sona gives you. So if you do that study and you wanted to do it for Sona credits, if they give you 2 Sona credits, I would double that to 4 points in this class. So you can get up to 8 points of extra credit in the class. So just keep that in mind. Okay, I'm going to do one more thing before we get going. I'm going to create 2 different breakout rooms. I'm going to have a question for each of you, for each room. So I'm going to do that right now. Okay, so if I'm going to come into each room one at a time and tell you what your question is. So just hang tight. Are in group 1, and I want you to remember that. Okay, so you're group 1, and I've got 2 questions for you. I don't expect you to know the answers, but I do want you to write down your best guess to these questions. Okay, the first question is this: is the Mississippi River longer or shorter than 500 miles? I want you to note or write down what your answer is to this question. So is the Mississippi River longer or shorter than 500 miles? And once you've answered that question, then the next question is, how long do you think the Mississippi River is? Again, I don't expect anyone to know, but write down your best guess for how long you think the Mississippi River is. Okay. Later on in the course, in today's lecture, I'm going to come back and I'm going to ask you your answers. Remember, you are group 1. All right, I'm going to go to the other breakout room, and I'm going to bring you back to the main room in a few moments.
Professor, you're on mute.
I realize that. Okay, got it. Thanks. You guys are in group 2, so you're going to need to know that in a few minutes. Just remember that you're in group 2. Okay. I've got 2 questions for you. I want you to write down your answers to these questions. I don't expect you to know the answers, so give it your best guess. First question is this: is the Mississippi River longer or shorter than 3,000 miles? Okay, just write down somewhere if you think it's longer or shorter than 3,000 miles. And once you've answered that question, then I want you to answer the next question, which is, how long in miles do you think the Mississippi River actually is? Write down your best guess. Okay. In a few minutes, later on in the lecture, I'm going to ask you for your answers. Just remember that you are group 2. Okay. All right. I'm going to close down the breakout rooms and bring everyone back to the main room. Okay, I think everybody is back in the main room. Okay, so I'm going to ask you your answers to those questions in a few minutes. Just remember your group number for now. But before we get there, let's continue with lecture. Oops. So last class, we had started talking about a sub-area of social psychology known as social cognition, which refers to how we think about the social world. And so far, we've been talking about, or as of last class, we were talking about 3 different biases we engage in when we think about things. In particular, we looked at the confirmation bias, which is the tendency to look only for information that supports what you already believe and not to look for information that is different from what you already believe. We looked at belief perseverance, which is the tendency to hold on to your beliefs even after they've been discredited. And we looked at self-fulfilling prophecies, whereby an initial false belief that something is true can lead to its own fulfillment. And we can use our knowledge of all 3 of those biases to answer the question of why it is that first impressions are so important. In other words, when you form an impression of someone when you first meet them, once you form that impression, it becomes difficult to change that impression later on. And conversely, if someone meets you, the first impression they have of you can become difficult to change for numerous reasons. And we can look at 3 of those reasons right now. So first off, let's say that someone's met you and they've formed an impression of you. Well, once they formed an impression of you, they're only going to tend to look for information that's consistent with that initial impression. They're going to tend to ignore other information. Or if they come across ambiguous information about you, they're going to tend to interpret it in a manner consistent with what they already believe. So if you make a bad first impression of someone and they think that you're a rude person, for instance, because of this bad first impression, they're only going to look for information that already supports that belief due to the confirmation bias. So that's one reason why it's very difficult to change a first impression. A second reason is that even if they encounter information that goes against their initial belief, that contradicts their initial belief, we know that from belief perseverance, people still tend to cling on to that initial belief, right? Even if it's been completely discredited. So people are very resistant, in other words, to changing their beliefs. And thirdly, if people have a false belief about you, We've seen with self-fulfilling prophecies how that false belief can lead them to behave in ways towards you that gets you to elicit behaviors that confirm that initial belief. So I gave an example this last class. So if someone believes that you're rude mistakenly, and they don't talk to you because they think you're rude, and you start to realize they're not talking to you, so you don't talk to them. And when you don't talk to them, they conclude, therefore, they were right, that this person's actually rude, right? So in other words, all of these biases contribute to this phenomenon whereby first impressions tend to be difficult to change. And we're still going to talk this class about other sorts of biases in the way that we make decisions and the way that we think, but they're going to fall under a class of biases that are known as heuristics. I want to tell you or describe what a heuristic is. So there's a lot of judgments we make that would normally be very complex in order to make them. They'd require us integrating a whole lot of information together to come to the best possible conclusion or the best possible judgment. A heuristic is a way to simplify a very complex decision-making process or a complex judgment. It's kind of like a rule of thumb or a shortcut that we use. And I'll give you an example of how this would work, okay? So let's say that you are cooking dinner tonight for family or friends or significant other or whatever. And you go to the grocery store after this class to pick up some wine for that dinner. And when you get there, there's only 2 types of wine left, okay? And you've got to pick one of these 2 types of wine. And the question is, which one is going to be better? Is it going to be this one? Or is it going to be this one? Now, chances are, if you're like 99.9% of people, you're of course going to say, well, the bottled wine is obviously better than the box wine, right? And probably most of the time, you're going to be correct. But how did you make that judgment? I mean, after all, you probably can't even read the label on this bottle. And even if you could, you probably don't know anything about its history. If you want to evaluate wine, you might need to know what year it is, what were the weather conditions when the grapes were growing, you know, all these sorts of things. You can't possibly know all this information. What you did instead of making a complex judgment that would require all that information is you relied on a rule of thumb. And that rule of thumb is that bottled wine is better than boxed wine. And you're not always going to be correct. There are some really bad bottled wines, right? And there's probably a few pretty good boxed wines. But usually you will be correct. And that's exactly what a heuristic is. It's a shortcut that we use to make a complex judgment. And that shortcut will usually lead us to the correct answer, but not always. We will make systematic mistakes when we rely on heuristics every now and then. And that's what we as social psychologists are particularly interested in, is when the use of these heuristics lead people to make mistakes. Now, people use or rely on heuristics for numerous reasons. One simple reason, just like in the example we saw, is that maybe people just don't have all the information that they need in order to make that complex judgment. Like you didn't have the information about the year of the wine and the weather conditions when the grapes were growing and that sort of thing. You didn't have that information, so you had to rely on some sort of heuristic. But even if we do have all the information needed to make this complex judgment, we may not use it for a couple of reasons. First off, social psychologists tend to think of people, at least sometimes, as being what are known as cognitive misers. A miser is someone who's cheap. So a cognitive miser is someone who's cheap with their cognitive resources. In other words, you might have the ability to think and to make complex judgments, but we don't really like to spend those cognitive resources if we can avoid it. We don't really like to think, in other words. So for instance, you could add 86 and 94 right now in your head, but you probably didn't. And the reason for that is because you don't really like to think a whole lot. In fact, this is going to be another one of these general themes that we see again pop up over and over in this class, is that people don't really, for the most part, like to think too in depth a lot of the time. There are always exceptions to this. There are certain people who do like to think in depth. There are certain situations in which we're more motivated to think in depth, and we're going to look at some of those situations when we look at persuasion. But as a general rule, we don't like to think if we can avoid it. And so if we have the option of making a really complex judgment or relying on a rule of thumb that's going to be right 95% of the time, we'll usually just rely on the rule of thumb. It's just a much easier way of making a decision. A second related reason for why people rely on heuristics is that even if we wanted to spend cognitive resources thinking about something in depth, we often can't because our brains can only hold so much information at a given time. Maybe when you were looking to buy some wine for tonight, you were able or you wanted to make the most informed decision possible which type of wine is better. You wanted to use all this information and integrate it to figure out which wine is better, but you're in a bit of a rush and you have to plan a menu. And you're worried about this promotion that's going on, and maybe you've got to pick up a kid after daycare or something, and you've got all these sorts of things that are on your mind, and there's only so much our brains can think about at any given time. And so we're limited in how much information we can process at a given time, right? In other words, we're limited processing, or we have limited processing capacity. Okay, so we rely on heuristics all the time to free up these cognitive resources. And it's not, and the point I want to make here is that using heuristics is not in and of itself irrational. It's not illogical. It makes sense why we do it. There's benefits to relying on heuristics. And usually that will lead you to the correct answer if you rely on heuristics, but not always. Not always. There are many situations in which you'll come to the incorrect conclusion because you relied on heuristic. That's what we're going to focus on in this class. So give me your opinions of this in the chat. So what do you think kills more people, lightning or tornadoes? And write what you think the answer is in the chat. Okay, so it looks like people are generally mostly saying tornadoes. Remember last class, I told you the general rule of thumb in this class, which is that if most people think something in this class, it's probably wrong. Well, that's going to hold for right now as well. It turns out that lightning kills more people than tornadoes, although you guys are kind of a microcosm of people in general. Most people think tornadoes kill more people. In fact, lightning kills more people. But most people are led systematically to the wrong answer here. We're going to look at why that's the case. Let's look at some more. But now you kind of know what's happening with these questions. So whatever, in the future, whatever question I ask you, whatever response option seems like it's wrong, you're going to know is the right answer, right? So what's more likely, dying as a result of falling airplane parts or dying as a result of a shark attack? Okay, well, you probably know what's going to happen here. Dying as a result of falling airplane parts is about 30 times more likely to kill you than dying from a shark attack. In fact, dying from a shark attack is extraordinarily rare. I mean, unbelievably rare. It is extremely rare that sharks actually kill people. But people drastically overestimate the likelihood of dying from a shark attack. Okay, this is a little old, back from 1998. Which of the products annually has the most associated injuries? Playground equipment, home workshop power saws, cooking ranges and ovens, beds, mattresses, and pillows. Okay, well, let's look. We actually have the numbers for this year. So these are the number of people who were associated or had an injury associated with this thing. So almost 250,000 people were injured with playground equipment. A little less than 100,000 people injured by workshop power saws. Just under 45,000 people injured with ranges and ovens. And over 450,000 people injured by beds, mattresses, and pillows. Don't ask me how. Although I did just read a stat that there's a certain number of people who strangle themselves to death by their sheets in bed, which is not something you want to think about when you're going to sleep at night, but there we go. Which of the following elicits the most injuries? This is from 1997. Scissors, hammers, chainsaws, or toilets? Well, we have the numbers for this as well. About 30,000 with scissors, 41,000 hammers, almost 30,000 with chainsaws, and over 44,000 people injured themselves with toilets. Now, this feels contrary to what we would expect, right? But think about this in a slightly different way. Think about the last time you used a toilet and think about the last time you used a chainsaw, okay? If you're using chainsaws more than toilets, you're either using chainsaws too much or toilets too little, okay? So in other words, there's simply more opportunity to injure ourselves with things like toilets because people use them multiple times per day. You can guess, put your guesses to this in the chat as well. And some of you might know this from legal psychology classes, but what percentage of people, so when people go to trial, defendants in a criminal case, what percentage of them plead insanity? They take the insanity defense. Does anyone know the answer to this? Feel free to guess in the chat. There's a guess of 10%, 35%, 50, 30, 90. Okay, guesses all over the place. 20, 5, okay. You're all wrong. Less than 1%. It's extremely rare that people plead insanity. But people drastically overestimate just how often this occurs. It's actually an extremely rare defense that people actually take. Okay, so the questions that I've just given you are questions that most people get wrong, okay? Or at least they find surprising when they hear what the right answer is. And the reason for this is because the process that most people use when answering this question is they rely on a heuristic. And that heuristic leads them to the wrong answer in these cases. And that heuristic is something known as the availability heuristic. Let me tell you what this is. The availability heuristic occurs whenever we have to estimate how frequently something happens or how likely something happens. One way that we have of doing this, if you have to estimate, for instance, how frequently do people die in tornadoes versus by lightning? Well, we don't know we don't have the statistics on this offhand, right? So how do we actually make that decision? Well, what people tend to do is they think of how easily they can come up with examples of people dying from from tornadoes, and how easily they can think of examples of people dying from lightning. And they compare them. And if you can easily think of examples of something, we assume it happens all the time. So in other words, we estimate the frequency with which something happens by how easily we can think of examples of that thing happening. The easier it is to think of an example, the more frequent we assume that it actually occurs. And so for most people, they have an easier time thinking of people who died from tornadoes versus thinking of people who died from lightning. And so therefore, we assume tornadoes kill more people. It's easier to think of examples of people being injured by power saws or on playground equipment than it is to think of people being injured in beds, right? It's easier to think of people being injured by chainsaws than it is to think of people being injured by toilets. So we think these things occur more frequently, when in fact, that's not always the case. And that's because how easily you can think of an example of something is based on a number of factors. So, for instance, the ease with which you can come up with an example of something, the ease with which you can think of something happening, is in part based on how frequently that thing occurs. And this is why we rely on the heuristic, because it's sometimes accurate. So for instance, when I went to grad school, I lived in Iowa for 5 years. And during that time, I never experienced a hurricane. And if you had asked me, what's the likelihood that Iowa gets hit by hurricanes? Well, I could not think of a single example of Iowa getting hit by a hurricane. So I would therefore, if I relied on the availability heuristic, I would say the frequency is actually pretty low, the likelihood's low. And when I moved to Miami, I can think of lots of examples since I've lived here of being hit by a hurricane. And because I can think of a lot of examples, I assume it must happen frequently. And you know what? I'd be more or less correct that we're much more likely to be hit by a hurricane in Miami than in Iowa, right? So this is why we rely on the availability heuristic, because in a sense, it can lead to the correct answer, right? However, the likelihood that we can think of an example of something is not only based on how frequently that thing occurs, it's also based on a bunch of other things. And it's these other things that can lead us to come to incorrect conclusions when we rely on the availability heuristic. So for instance, the media, the news media, for instance, will tend to have stories about certain types of events way more than stories about other events. As an example, when a plane crashes, that's all over the news, right? When someone dies from a heart attack, that's not on the news at all. So because of that, we're always exposed to things like plane crashes or train crashes or car crashes. That's always on the news. And we're very rarely exposed to people dying from heart attacks. As a consequence, when you ask people what's more likely to kill people, car accidents or heart attacks, a lot of people mistakenly believe car accidents are more likely to kill people because they can easily think of lots of examples of car accidents. They're all over the news. In reality, heart attacks or heart disease in general is way more likely to kill most people. It's one of the top killers is heart disease, right? But people don't realize that because we don't really hear about people dying from heart disease, in part because it is so common, right? So because of that, we misestimate how frequently those things occur. Furthermore, the ease with which you can think of something happening is also based on how frequently that, or sorry, how recent in the past that thing has happened. So things that have happened in the past, let's say a couple weeks, you can easily think of those things happening because they just occurred. They're fresh in your mind. As a consequence, things that have happened recently, we tend to overestimate their likelihood of occurring. If we take something like 9/11, for instance, well, after the terrorist attacks of 9/11, if you ask people how likely it is that they would die in a plane crash if they were to take a plane, they would probably think their odds of dying are way higher than they actually were. Okay? It turns out that even with the plane crashes of 9/11, even if you include those, your chances of dying in a plane crash are still astronomically small, even after that. But people overestimated that, in part because it was really, really easy to think of an example of a plane crash because we had just gone through this. Right? There were recent events that were overrepresented in memory. This is also partly why people have a tendency to think that the violent crime rate has been increasing. In fact, in reality, the violent crime rate's been decreasing for a number of years, for quite some time now, that we're getting more and more peaceful in general. But what happens is that violent acts that have occurred recently, let's take as an example the insurrection at the Capitol, right? Those sorts of violent events that have occurred recently are really easy to think of examples of. We can think of lots of examples of violence in the past year because they're fresh in our memories. I mean, the insurrection on the Capitol. But if I were to ask you, how many examples of violence can you remember from the year 2013? You might struggle a little bit with that, right? Not because they don't occur, but because you've just simply forgotten what happened in 2013. So because it's easier to think of recent examples of violence rather than past examples of violence, it feels as if violence is on the increase. But in fact, the only reason you can think of recent examples of violence is not because there's more violence, but because it's fresher in your memory. And so relying on the availability heuristic leads people to the wrong conclusion. Finally, things come to mind more easily if our attention is directed to those things. So for instance, let's say that as a hobby, I like reading about airplane crashes for whatever reason, right? So I know all about like dozens and dozens of airplane crashes that have occurred. Okay? Well, if you were to ask me then, how likely is it that I would die in a plane crash? I might overestimate that likelihood because I can easily think of examples of plane crashes because I research them all the time. They come to mind easily. So if I'm relying on the availability heuristic, if they come to mind easily, I assume they happen all the time. And so I might overestimate my likelihood of dying in a plane crash. Okay. So, so again, the availability heuristic occurs when we're trying to estimate the likelihood of something happening or the frequency with which something happens. And we simply do so by thinking of examples of that thing happening. If it's easy to think of examples, we think it happens all the time. If it's difficult to think of examples, we think it doesn't happen very often at all. We can use the availability heuristic in conjunction with what we know about confirmation biases to explain certain pseudoscientific beliefs that people have. And I'll give you one example here. The belief that weird things are more likely to happen when there's a full moon versus when there's not a full moon. Now, there's no reason why that should be the case. The full moon doesn't mean the moon is closer and is exerting more tidal forces or anything like that, right? All a full moon means is that the moon, the earth, and the sun are lined up in a particular orientation. That's all that it means. It doesn't mean it's closer. There's no more extra tides during a full moon or anything like that, okay? So there's no reason why this would be the case, but some people do think that weird things are more likely to happen during a full moon. Why is that the case? Well, remember, because of confirmation biases, people only look for information that supports what they already believe, right? So if I believe that weird things happen during a full moon, I'm paying attention anytime something weird happens during a full moon. And maybe I can remember 5 instances of this happening, that weird things happen during the full moon. There's 5 times I can remember that happening. Those examples come to mind easily. And so if I'm relying on the availability heuristic, well, if I can easily think of examples of weird things happening during a full moon, I assume it happens all the time. The problem is, because of confirmation biases, I'm only paying attention to when weird things happen during a full moon. I'm not paying attention to when weird things happen when there isn't a full moon, or when there's a full moon and nothing weird happens. or when there's no full moon and nothing weird happens. I'm not paying attention to those instances because of confirmation biases. I'm only paying attention to these 5. So these are the only 5 instances I have available. But the thing is, had I been paying attention to all these other instances, maybe I would have come up with something like this. Had I been paying attention, maybe I would have realized that there were 60 times when a weird thing happened and there wasn't a full moon. And there were 60 times there's a full moon and nothing weird happened. And suddenly, in the context of these numbers, the fact that 5 times a weird thing happened during a full moon doesn't seem all that remarkable, right? What's happening is that weird things happen every now and then. Sometimes there's a full moon, sometimes there's not. And so sometimes by coincidence, there's going to be a full moon when weird things happen. That doesn't mean there's an actual association between those two things, right? But because of confirmation biases, we're only ever paying attention to those 5 instances, which leads us to this conclusion, this false conclusion, that weird things are more likely to happen during a full moon. Okay. And we can use the same sort of logic to explain all sorts of beliefs that people have that are incorrect. And I'll give you another one that most people, I think, in this culture believe. And I imagine that many, if not most of you, have this belief. I'm going to tell you that it's actually false. And that's the belief that kids, if they eat sugar, become more hyperactive. Okay? There's a very, very common belief that if you give kids candy, for instance, they get all hyper, right? Like a sugar rush. There is absolutely no scientific evidence for this whatsoever. Okay? If you don't believe me, you can Google this. You can Google like kids sugar hyperactivity myth, and all sorts of things will come up explaining that this is a myth. Okay? But the reason that people believe this, in part, is for the same reason that we just saw on the prior slide. Because what's sort of interesting about this one is that parents are the people who are most likely to believe in this, which is sort of weird because parents have the most data to rely on, right? It seems weird that if you give people more data, they're more likely to come to a wrong conclusion. How can that be? Well, what happens is that parents in particular, but everybody, because of confirmation biases, if they believe that giving kids sugar makes them hyperactive, then that's what they look for. That's what they remember. All the times their kid was hyperactive after they'd eaten sugar. And there's 10 times they can come up with where that happened, right? And it's easy to think of examples, so they assume it happens all the time. But what they weren't paying attention to is all the times they gave their kids sugar and they weren't hyper. And all the times their kids were hyperactive when they weren't given sugar. And maybe if they'd been paying attention to those instances, they would have seen something like this, that there were 100 times their kid had sugar and they weren't hyperactive. There were 100 times they were hyperactive when they didn't have sugar, right? And again, suddenly what we see is that in the context of all these numbers, the 10 times that the kid was hyper after eating sugar doesn't seem all that remarkable. Sometimes kids are hyper and sometimes they're calm. Sometimes they eat sugar and sometimes they don't. So sometimes by coincidence, those things are going to overlap. But again, it doesn't mean that there's a causal link between them. And so because of this process of confirmation biases, only focusing on these 10 instances, and because of availability heuristics, where we judge how frequently this occurs based on how easily we can think of examples, that leads people to make these wrong conclusions, to believe that things are associated when in fact they're actually not. Oh, by the way, there's another reason people believe in this myth apart from this as well, which is that a lot of the contexts in which kids have sugar are contexts that make them hyper. So for instance, when do kids have sugar? Birthday parties. They have cake and ice cream, right? And so kids often are kind of hyper at birthday parties, but not because of the sugar, because they're at a birthday party. That's why they tend to be hyper. Okay, and there's all sorts of beliefs that can be explained in very, very similar ways. There are numerous consequences to the availability heuristic. First off, it's actually related to something we've seen before. If you remember the false consensus effect, remember the false consensus effect is the tendency to overestimate how many other people have the same opinions as us, right? Well, part of the reason the false consensus effect exists is due to the availability heuristic. So for instance, let's say that you have some sort of political belief. Let's say that you are, you want to abolish the death penalty or whatever it is, doesn't matter. Let's say you want to get rid of the death penalty. And I ask you to think, how many other people also believe what you believe? Well, you start thinking, how easily can I think of examples of people who want to abolish the death penalty? What comes to mind most frequently are our friends' opinions, because that's who we spend the most time with, right? So it's our friends' opinions that come to mind. But the thing is, our friends, we pick our friends based on how similar they are to us. We're going to see that when we look at attraction later on. So our friends tend to be quite similar to us already. So the very people's opinions who happen to come to mind are people who tend to be just like us and therefore who agree with us. And so you tend to only be able to think of people who agree with you because you hang out with people who are very similar to you. So because of the availability heuristic, it's easy to think of people who agree with you. Therefore, we overestimate how many people share our opinions. It leads to the false consensus effect. The availability heuristic is also related to something known as the base rate fallacy. The base rate fallacy is something that most people tend to fall prey to, which is that people tend to be relatively insensitive to numbers, numerical base rate information. Okay? In other words, what influences us are stories. What doesn't influence us are just data, right? Statistics. That doesn't really have an impact on us. So let's say that you are interested in buying a car. So you're looking at Hondas in particular, okay? And let's say that you know statistically in surveys of 100,000 people who have bought Hondas, 90% of them are happy with their car. Okay? So on the one hand, you have all this data from 10,000 people about whether they like Hondas. On the other hand, you have a single friend who had a bad experience one time with the Honda. What's going to be more impactful on your decision? The data from 10,000 people or your single friend? Well, most people are more impacted by their single friend because we're just insensitive to base rate information. We're insensitive to statistical information that doesn't really impact us, but single stories do. And the reason for that, in part, is because it's easy to think of stories, right? Stories come to mind easily. Statistics don't come to mind easily, right? As a consequence, because stories come to mind easily, so I can think of a friend who had a really bad experience with a Honda, because of the availability heuristic, I assume that means people must have bad experiences all the time. Okay? So relying on the availability heuristic leads people to ignore the information they should actually be paying attention to, the data, the statistics, right? That's what the base rate fallacy is, the tendency to ignore that numeric information. This happens all the time. People are really, really bad at estimating the likelihood of a whole bunch of things, especially of low frequency events. So for instance, people vastly overestimate the likelihood of plane crashes. I kind of alluded to this. Flying by plane is incredibly safe, okay? There are multiple levels of redundancy and there's all sorts of safety features in planes. Dying in car crashes, much less safe, right? But when you ask people, people tend to be more fearful of dying from plane crashes rather than car crashes. In part, this is because when a plane crashes, as I mentioned, it's all over the news, right? It's easy to think of examples of plane crashes. It's really, really easy. So we think they happen all the time. But what you don't hear about are the hundreds and hundreds and hundreds of planes that land safely every single day, right? So what comes to mind are specifically plane crashes. We overestimate their likelihood of occurring. In fact, if you've ever had a friend drop you off at the airport because you're flying somewhere, the last thing they say almost every time, have a safe flight, right? Well, it turns out that they are more likely to die in a car crash on the way home from dropping you off at the airport than you are to die in that plane. So what you should be doing is wishing them a safe drive home rather than wishing you a safe flight. People are also really bad at overestimating their likelihood of winning the lottery, which is why so many people play the lottery. The lottery is a horrible game to play in terms of your actual expectation of winning in the long run. You're much better off going to a casino and playing games there. Not that you should do that either, because they rig that for the house as well. But you still have a much better chance of winning at the casino than you do of winning the lottery. And part of the reason for that is because when someone wins the lottery, they're all over the news. And you hear about the Powerball winner that just won $100 million. But what you don't hear on the news are the 20 million people who lost, right? You don't hear their stories. So what comes to mind are only the winners, which makes you overestimate the likelihood of winning the lottery. Okay? In fact, there's a really interesting statistic I heard once, that if you look at the really big lotteries, where you get like a whole bunch of people playing them, let's say that you drive to a gas station to buy a lottery ticket. Well, driving to a gas station involves driving a car, which puts you at risk of dying in an accident. And what some studies have shown is that your likelihood of winning the lottery is about the same of your likelihood of dying in a car accident on the way to buy your lottery ticket. So by playing the lottery, you are literally gambling you're not going to die on the way to buying that lottery ticket. Okay, so that was the availability heuristic, but I want to talk about a couple of other heuristics. And the first one I want to talk about has to do with the question that I asked you guys at the beginning of class. So what I want you to do is open up your Top Hat account, and we're going to get your responses to the question. I asked everybody how long the Mississippi River is. I want to get your responses to this question. We're going to do that through Top Hat. So open up that account. And what I want you to do, I told you to remember what group you're in. I only want group 1 people to respond, okay? Group 2 people, I'll give you your chance to respond in a second. So group 1 people, whatever number you wrote down for how long the Mississippi River is, I want you to tell me if that number is longer than 2,000 miles, or sorry, less than 2,000 miles or equal to or greater than 2,000 miles. So just group 1 people. So what was the number you put down? Less than 2,000 or equal to or greater than 2,000? Okay, looks like about half of the people responded, so that's good. I won't look at the responses just yet. Let's do the same thing for group 2 people. Okay, so only group 2 people, same question. Okay, anyone else? Okay, looks like that's everybody. Okay, so let's look at the responses that you guys gave. So group 2 people. Okay, so the majority of group 2 people, it's only 12 people, but the majority of them, 75%, said it was greater than or equal to 2,000 miles. Okay, let's look at what the group 1 people said. Whoops, sorry, hang on. How can I go back here? Okay, I'm just gonna exit in that case. There we go. Okay, what did the group 1 people say? Different responses. Okay, so now the majority of people are saying it's less than 2,000 miles. So this is a bit weird because it's the exact same question I asked you. How long is the Mississippi River? So why are we getting such different answers? Why are the group 1 people saying it's shorter than the group 2 people? Well, that's partly because the first question that I gave everybody was slightly different in each of these cases. Okay, so for the group 1 people, oops, hang on one second. I think I forgot to share my slides. Hold on. There we go. So for the group 1 people, the first question I asked you was whether the Mississippi River was longer or shorter than 500 miles. And then you gave me an answer of how long you thought it was. For the group 2 people, I asked you first whether you thought the Mississippi River was longer or shorter than 3,000 miles before I asked you how long you thought it was. And that's the only thing that differed between the 2 groups, right? So it seems like your estimates of how long the Mississippi River was somehow biased by whatever that first question was that I gave you. In particular, if the first question was, is it longer or shorter than 500 miles, you gave ultimately a shorter estimate of the length of the Mississippi River than if the first question I'd given you was whether it's longer or shorter than 3,000 miles. Your estimates were influenced by that initial value, right? What you've done is you've fallen prey to what's known as the anchoring and adjustment heuristic. By the way, the actual length of the Mississippi River is somewhere, it's something around 2,300 miles, I think, something like that. But what you used to come to your conclusion, a lot of you, if not most of you, was likely the anchoring and adjustment heuristic. Let me describe to you what this is. So anchoring and adjustment occurs whenever you have to give some numeric estimate of something. So how long is the Mississippi River? Or it could be how high something is, how far something is, how much something weighs, how old something is. Anytime you have to give a numeric estimate, that's when we rely on anchoring and adjusting. What we do is that when we don't know what that numeric value is of something, then we look for what's called an anchor. An anchor is just a known numeric value. Okay, I'll give you an example, then I'll relate it back to the Mississippi River in a second. So you know that water freezes at 32 degrees Fahrenheit. Okay? So my question is, at what temperature does vodka freeze? And feel free to put guesses in the chat. At what temperature do you think vodka freezes? Yeah, someone always says it doesn't freeze. No, it'll freeze. If you get it cold enough, it'll freeze. And you might be saying that because you have a bottle of vodka in your freezer right now and you know it's not frozen. But if you get it cold enough, it will freeze. Anyone else want to guess? I see a couple of people saying 10 degrees, 0, 25. Okay. Now, the main point is how you came to this conclusion, right? Now, the actual temperature at which vodka freezes depends on its purity. It's somewhere, depending on the purity, between something like, I think it's like -16 and -40, something like that, depending on its purity. Okay. But with the exception of Carolina, who is actually pretty close there, -20, it looks like everyone else was a little bit off. And that's actually good because your estimates were actually very consistent with what people actually do. So how did you answer this question? Well, what you probably did, you probably don't know what temperature vodka freezes at, but you do know that water freezes at 32 degrees, right? And you know that water freezes in your freezer, but vodka doesn't. So vodka has to freeze at a lower temperature than 32 degrees, right? So what you've done is you've identified an anchor. The anchor is 32 degrees. And you know it has to be lower than 32 degrees. So you start adjusting down from that anchor. Okay? But one of the key aspects when people rely on the anchoring and adjustment heuristic is that the adjustments they make from that anchor are insufficient usually, meaning people don't go far enough from the anchor. And that's exactly what we saw here. So the anchor was 32. Now, in order to give me the right answer, you had to go down to at least -16, right? But most people didn't adjust far enough from the anchor. So you might have given me estimates of 10 degrees or 0 degrees, which isn't adjusting far enough, right? So what you guys did is in line with what most people do when engaging in the anchoring and adjustment heuristic. Okay, so there's really two key aspects to this heuristic. The first is that we look for an anchor when we try to give a numerical estimate. And the anchor that you land on will in part determine your final estimate. And secondly, that our adjustments we make from that anchor usually don't go far enough. They're insufficient. And so what that means is for the Mississippi River, when you had to estimate how long it was, you probably had no idea. But you did know one anchor. The anchor was the number that I gave you. If you were in group 1, I asked you if it's longer or shorter than 500 miles. And so you glommed onto that anchor. That was your anchor, right? Then maybe you adjust from there. Maybe you think it's a little bit more than 500 miles. So you guess 1,000 miles. On the other hand, if you were in group 2, the first question I asked was, is it greater, shorter, or longer than 3,000 miles? Well, that's your anchor now. You're starting at a higher anchor, right? Because you're starting at a higher anchor, you tend to give higher final estimates than people who started from a lower anchor, even though that anchor gave you no clues as to how long the Mississippi River was, right? There's no reason to think that 500 or 3,000 or whatever number I arbitrarily gave you had anything to do with how long the river was, but you still used it as an anchor in your final estimates. And we see this all the time with people. I'll give you some examples of that. So this was a study where people were asked the following question: what percentage of African countries are in the United Nations? And most people have no idea, right? So what the researchers did, though, is before they got people to give their estimates, what they did is they had sort of this like this modified roulette wheel type thing, but they rigged it. And they rigged it such that when they spun it, which made it look like it was a random selection of numbers to the participant when they spun this wheel, but they rigged it such that that wheel would only come up with one of two numbers, either 10 or 65. Okay. So what the researchers did is they randomly assigned participants to spin this wheel and it would come up with either 10 or 65. But from the participant's perspective, it's just a completely random number to them. The researchers then asked participants, okay, whatever number came up, is it higher or lower than that apparently random number? And people would say higher or lower. And then they would ask them for their actual estimate. So it's very, very similar to what I did with you with the Mississippi River, right? Now, obviously, the number that comes up, whether it's 10 or 65, from the participant's point of view, that's a completely arbitrary number. It has no bearing whatsoever on the actual percentage of African countries that are in the UN. It should have no impact whatsoever on their final estimates, right? And yet, What they showed is that when the supposedly random number was 10, people estimated 25% of African countries. When that random number was 65, the estimate was 45% of countries were in the UN. In other words, people's final estimates were drastically affected by this completely random number that came from this roulette wheel. Why is that the case? Well, because these people had no idea what the correct answer was. And they were looking for an anchor. And the only anchor they had was this completely random number that came up. And even though that number had nothing to do with the actual answer, it's the only anchor they had. So they relied on that anchor. And as a consequence, a larger anchor resulted in a larger estimate. Okay, so this demonstrates a couple things. First off, that whatever anchor we use in part determines the final estimate that we give. And secondly, that people will use even completely random numbers as anchors if they have nothing else. Yeah, so as Karen says, people can be weird. Yeah, so people are kind of weird, but they're weird in a predictable way, right? They're predictably weird. They seem to make what seems like irrational decisions, but predictably so. We know why they're making those decisions. And keep in mind that anchoring and adjustment will often work. It often makes sense, right? When you have to estimate what temperature vodka freezes at, it makes sense to use an anchor of 32 degrees. You know it has to be lower than that. So that it makes sense to rely on those anchors. It's just that in certain situations like this one, where people have no idea what the correct answer is, those anchors seem to inappropriately influence them. Oh yeah. So imagine that you have to make the following calculation. And then I take it away, okay? Now let's imagine that I did that for you guys in this class, and I ask you to estimate what is the product of that equation that I just put up there, and you give me a number, okay? And let's say that in another class that I have, I show them this equation. Keep that up there for a few seconds, and I take it away, okay? And I have them give an estimate of what the product of that equation is. Turns out that when you do this, people will come up with very, very different estimates of what that product is. Now, if we look at what those two equations were back to back, the first one is simply 1 times 2 times 3 times 4 all the way to 8. And the second one is simply 8 times 7 times 6 times 5 all the way to 1. And we know that based on the rules of multiplication, it doesn't matter the order in which you multiply numbers. So these equations, you know, have to be identical, have to equal the exact same value. It's just, you're just mixing up the numbers, right? So we know that in reality, the equations are equal. But when you ask people to give their estimates of these equations, they give you very, very different estimates. When people are shown the first sequence for a few seconds, the median answer, and the median is simply means the answer that's the halfway point. So if 100 people give you an answer, it's the answer that's right in the middle that the 50th person gave. So the median answer for the first sequence is about 512. The median answer for people who get the second sequence is 2,250. Very, very different, right? Why is that the case? Well, imagine that you're in this first condition. So I show you this first equation, and I give you a few seconds to answer it. So you start calculating. Okay, let's see. 1 times 2 is 2. 2 times 3 is 6. 6 times 4 is 24. 24 times 5 is 120, and then it disappears. Okay, well, you have to estimate a numerical value, right? So what do? Well, you rely on an anchor. What's the anchor that you have? Well, so far you've got 120 is what you've calculated so far. You know, there's a few numbers left, so it has to be somewhat greater than 120. So you adjust upwards from that anchor of 120, and you get to 512. That's your estimate, somewhere in there. On the other hand, people in the second group, they start calculating 8 times 7 is 56. 56 times 6 is what, 336? And it disappears. Now their anchor is higher than the anchor of people in the first group. It's 336, right? So they know they have to adjust upwards from that anchor. So they estimate maybe it's about 2,000, somewhere in there. So because they're starting with a higher anchor, they end up with a higher estimate. Okay, so that's the first point I want to make, is that the anchor that you start with in part determines the ultimate estimate you end up with. So a higher anchor equals a higher estimate. And the second part that I mentioned, second characteristic of this heuristic, is that people don't adjust enough. Well, we see that here as well. The correct answer is actually over 40,000. But people tend not to adjust enough from that anchor. So if their anchor is 120, they adjust it up to 500. That's not enough, right? If their anchor was 336, they adjust it to 2000. Again, that's not enough. So we see again that people are not adjusting enough from the anchor they're given. Okay. Another heuristic I'll mention is, this one's a little bit more complicated, something called the representativeness heuristic. And here's the basic idea of the representativeness heuristic. Well, first off, let me have you answer a couple questions. So imagine that you flip a coin 10 times in a row. Which outcome is more likely? So this is a sequence of heads and tails. So the first sequence is heads, tails, tails, heads, tails, heads, heads, tails, tails, heads. And the second sequence, let's say, is heads, 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 heads. Now, if you were to flip a coin 10 times in a row, which of these two outcomes is more likely to actually occur? Any guesses in the chat? The first or the second? Okay, so a few people say sequence one. A few people say they're exactly the same. Yeah, they're exactly the same. They're exactly the same likelihood of coming up. Assuming that heads and tails occur equally often, 50-50, it's exactly the same likelihood of coming up. Although most people think that the first sequence is actually more likely to occur. Now, if you want to realize why they're the same likelihood, well, think of this first sequence, right? In order for you to get this first sequence, your first coin flip has to be a heads, right? So you've got a 50% chance of that. Your second coin flip has to be a tails. You've got a 50% chance of that. Your third coin flip has to be a tails. There's a 50% chance of that, right? If you look at the second sequence, you come to the same conclusion. The first flip has to be a heads. There's a 50% chance of that. The second flip has to be a heads. There's a 50% chance of that, et cetera, et cetera. On every flip, you've got exactly a 50-50 chance of it coming up in order to match that sequence, right? So the consequence, both sequences are exactly likely to occur. But most people think the first sequence is more likely to occur. Why? What cognitive process are you using that's leading you to that incorrect answer? We're going to come back to that. Or imagine that you go to buy a lottery ticket. Let's say that this lottery works in such a way that you've got to pick like 7 numbers between 1 and 50. Then they draw balls and they draw the numbers. And let's say that when you go to buy this lottery ticket, there's only 2 tickets left. One ticket has the numbers 1, 2, 3, 4, 5, 6, 7. And the other ticket has the numbers 3, 7, 11, 15, 22, 29, 34. Okay. Which of these 2 tickets would you prefer? In other words, which ticket is more likely to win the lottery? And if you're like most people, there's a gut feeling that you'd much prefer the second ticket than the first ticket. In other words, you have sort of this implicit belief at some level that this second ticket is more likely to win the lottery than is the first ticket. Now, in fact, these 2 tickets are exactly equally likely to win the lottery. It doesn't matter which of these 2 tickets you buy. But the vast majority of people will not only prefer to buy the second ticket, but they will pay more money in order to buy a ticket that has the exact same likelihood of winning as this first ticket. Why is that? Why are people coming to the wrong conclusion here? Let me give you one more hypothetical scenario. This one's a little bit more involved. Let's imagine that I've got a description of 100 people. So on a piece of paper, there's a description of 100, or each piece of paper has a description of one person. I've got 100 of those slips. I fold them up, I put them all in a big bowl. And the only thing you know going in is that of these 100 people, 30 of them are lawyers and 70 of them are engineers. Okay. So I shake it up in this big bowl. I pull out one at random. And the one at random I pull out, I open it up and I read the following. Twice divorced, Frank spends most of his free time hanging around the country club. His clubhouse bar conversations often center around his regrets of having tried to follow his father's footsteps. The long hours he had spent at academic drudgery would have been better invested in learning how to be less quarrelsome in his relations with other people. And my question to you is, do you think Frank is a lawyer or an engineer? Now, based on the information I gave you, and by the way, there's no right or wrong answer because there is no Frank, right? But just based on your gut feeling, do you think Frank is more likely to be a lawyer or an engineer? Feel free to guess in the chat. Anyone else want to guess? Again, there's no right or wrong answer. So you literally cannot be wrong on this. Okay, now, what I want you to do is think about how you came to that conclusion, right? If you thought he was a lawyer and engineer, how did you come to that conclusion? Now, if you're like most people, then what you did is you took this description of Frank and you compared it to what a typical lawyer is like and to what a typical engineer is like. And maybe you thought, well, let's see, academic drudgery, that kind of sounds like law school a little bit. Being quarrelsome, if you're argumentative, that's what lawyers make lots of arguments. That's kind of like a lawyer. He seems a little bit more like a lawyer than an engineer, so I assume he's a lawyer. If you're like most people, you did something like that to come to this conclusion. However, what most people don't do is consider this information up here, that of the 100 people, 30 of them were lawyers and 70 of them were engineers. So going into this, he's more than twice as likely to be an engineer. Okay. Now, it doesn't mean he's more likely to be an engineer after you get this information. But the point is, most people don't even use this initial information in their final assessments. Now, I can show mathematically, I'm not going to, but I could show mathematically that the numbers, this likelihood, how many people are lawyers to begin with, makes a huge difference in what the likelihood is that Frank is a lawyer or an engineer. Makes a huge difference. And so people should be using that information. But the vast majority of people almost completely ignore that information when deciding, in this case, if Frank is a lawyer or an engineer. Now, what's going on here? What leads people to the conclusions they're drawing in this hypothetical scenario, as well as with the coin flipping and with the lottery, is they're relying on what's known as the representativeness heuristic. Okay, this one's a little bit trickier than the other ones. But the basic idea with representativeness is that in some situations, we're trying to decide if something comes from category A or category B. Okay. And the way that we do that is we compare that thing to a typical member of each of those two categories. And we see how closely it resembles that member. And if it resembles the member closely from that category, we assume it comes from that category. So for instance, when you had to decide if Frank was a lawyer or an engineer, what you did is you compared Frank, the description of Frank, to what a typical lawyer is and to what a typical engineer is. If he seems more like a typical lawyer, then you'd assume he's a typical lawyer. Okay? What you didn't do is use the mathematical information that was relevant to you. In other words, you ignored the base rate. So we saw that earlier this class, the base rate fallacy, that people don't pay attention to statistics and numbers and the mathematical stuff that goes into this. Okay? And you probably did too. You probably, if you're like most people, ignored that statistical information that really does matter. And instead, you simply compared Frank to a typical lawyer and a typical engineer. And that's how you came to your conclusion. Similarly, people did something like this, usually, when answering the other questions as well. So you have to decide which of these two series of coin flips is more likely. Then what you might do is you have two categories. Here's a random sequence of coin flips category and a non-random series of coin flips. And you ask yourself, does this first sequence look like it's random or not random? Well, it looks like a typical random sequence of coin flips where you get a mixture of heads and tails usually. So we consider it to be random. On the other hand, getting 10 heads in a row, that doesn't seem like a typical random series of coin flips. So we put it into the non-random category. And therefore, when you're deciding which of these two series of coin flips is more likely, well, the first one looks more random than the second, so therefore it's probably more likely. That's how people come to that conclusion. Okay. What you didn't do is mathematically calculate the actual likelihood of those sequence of coin flips, right? That's not what we do. We tend not to pay attention to the mathematical base rate information. And so by relying on representativeness, that the first sequence of coin flips is more representative of what a random series of coin flips looks like, that led people to assume it is more random and therefore more likely, which is incorrect. Similarly, when people had to pick which lottery ticket they thought was more likely to win, they think, well, what does a winning lottery ticket look like? Let's say we have two categories, winning lottery tickets, losing lottery tickets. Well, a winning lottery ticket looks like a series of 7 random numbers, usually, right? So therefore, the second ticket, it resembles a winning lottery ticket more than the first lottery ticket, which has a very specific order to it. That doesn't look like a winning lottery ticket to us. So we assume that therefore, the second ticket is more likely to be a winning lottery ticket than the first ticket. even though they're exactly equally likely to actually win. Okay? So that's representativeness. We judge something that something is part of a category if it looks like a typical member of that category. And we ignore all the mathematical base rate statistical information. Okay? These ideas also apply to how we form impressions of others. And so in particular, when we look at stereotyping and prejudice later on in this course, we're going to see that a lot of the ideas that we're talking about now, the biases and heuristics that we've been discussing, are going to come back later on, as we're going to see. And it's partly for this reason why there are some people in this country especially, who when they come across someone who's dressed in, let's say, Middle Eastern clothes, like this guy, will jump to the conclusion this person is a terrorist. There's a lot of people in this country who unfortunately associate Middle Easterners with terrorists. And that's because they have a false belief. Well, first off, they have a false belief that most terrorists are Middle Eastern. Well, that's not the case. Most terrorists in this country are actually white people from this country. But people have a false belief that Middle Easterners are more likely to be terrorists. When they come across someone who's dressed like a Middle Easterner, and they have two categories, does he come from the terrorist or non-terrorist category? Well, if you believe erroneously that terrorists look Middle Eastern, and this guy looks Middle Eastern, he looks like a typical terrorist, and so we put him in that category. We assume he's a terrorist because he looks like a typical member of that category. But what that does is it ignores the fact that of all the people who dress this way, the vast, vast, vast majority of them are not terrorists, right? There are tens and tens and tens of millions of people who dress this way that are not terrorists, right? But people ignore that base rate information and assume they're a terrorist because it looks like a typical member of what they think a terrorist looks like, is the basic idea. Okay? So we're going to come back and talk about, when we look at stereotyping, and we're going to look at how all these ideas that we're talking about now come back and how they affect impressions of people. Okay. I'm going to stop lecture here, but before you go, we're going to have a quiz in Top Hat. So go back to your Top Hat account. And this is quiz number 3. And it has to do with stuff that we've talked about yesterday and today. Or not yesterday, last class, Tuesday and today. Let's get started. So John recently got a bad haircut. Now every time he goes out in public, he thinks that everyone notices how bad his hair looks, even though no one actually notices. John is likely experiencing which of the following? Is it self-presentation, spotlight effect, the hindsight bias, or belief perseverance? Yeah, in general, if your Top Hat freezes for whatever reason, just send me a private message over chat with your answers for each question, and I'll manually enter it. Okay, looks like everyone's answered. Okay, what I'm describing here is what's known as the spotlight effect. It's the tendency to feel like there's a spotlight on you and everyone can notice you when in fact, not everyone does notice you. Okay, so looks like most of you guys got that. That's good. Question number 2. Amanda behaves differently around her friends than she does at work because she pays attention to how she is coming across to others. Social psychologists would say that Amanda is it a low self-verifier, a high self-verifier, a low self-monitor, or a high self-monitor? You've got 10 seconds. 3, 2, 1. Okay, so last class we talked about self-monitoring as an individual difference variable. A self-monitor means someone who's scanning the environment to figure out how they should act, right? You're paying attention to how you're coming across to others, in other words. A low self-monitor is someone who's not doing that very much. A high self-monitor, such as Amanda, is someone who does do that a lot to see how she's coming across to others. So that's why D is the correct answer. Good. Question 3. After watching the presidential debate, so imagine this is before the election, Leslie, a Republican, thinks that Trump won the debate. However, Anthony, a Democrat, thinks that Biden won the debate. What social psychological phenomenon would explain why Leslie and Anthony came to opposite conclusions after watching the exact same debate? Confirmation bias, belief perseverance, self-fulfilling prophecies, or the availability heuristic? You've got 10 seconds. 3, 2, 1. Okay, so we talked about a study that was basically just like that. We talked about the study that had to do with Hannah. Remember that people watched Hannah's performance when answering a series of questions and came to exact opposite conclusions based on their pre-existing beliefs. And we explained that in terms of the confirmation bias, A. It's similar to belief perseverance, but it's not exactly the same. Belief perseverance would occur if you have a belief and then you encounter information that completely discredits that belief and you still cling on to it. In this hypothetical scenario, neither of these people came across information that completely discredits their belief. That's why belief perseverance isn't really relevant here. But confirmation bias is, because people are only looking for information that supports their pre-existing beliefs. So Leslie, who's the Republican, only looks for information that supports Trump, and Anthony, a Democrat, only looks for information that supports Biden, which leads them to opposite conclusions. Question 4, the first step of a self-fulfilling prophecy. Remember, there are 3 steps. The first step to a self-fulfilling prophecy is what? A person has a false belief, a person has a complex decision to make, a person comes across information that contradicts their beliefs, or a person provides reasons for why they have a specific belief. Got 10 seconds. 3, 2, 1. Okay, so when we talked about self-fulfilling prophecies, we mentioned that the first step is that a person has a false belief. They then treat the target in a manner consistent with that belief. It's the second step. And that target responds to that treatment in a way that confirms the initial belief. That's the third step. So the first step is a person has a false belief. Finally, last question. Which of the following statements about heuristics is not true? So 3 of them are true, 1 of them is not. A, heuristics are mental shortcuts. B, people often use heuristics because they don't like to think. C, heuristics usually lead to wrong conclusions. D, heuristics are useful when people have to make complex decisions. And you've got 10 seconds. 3, 2, 1. Okay, so we talked about this all today. And one of the points I was trying to get across is that heuristics are not illogical because they can often lead to correct conclusions. They sometimes lead to wrong conclusions, but usually they're correct. So C is the incorrect statement here. Okay, sorry, I'm a few minutes over, but I'll let you guys go now, and I will see you guys on Tuesday. So have a great weekend, and I'll see you then.